Welcome everybody, my name is Ricardo Vinuesa. Today I'm very excited to share our latest research. So I'm going to be talking to you about how to improve turbulence control through explainable deep learning. This builds a lot on some of our previous work trying to understand turbulence with explainable deep learning and at the same time trying to control it with deep reinforcement learning. Now today we're going to put both together and we're going to try to see how well we can control the flow using these techniques. This is research funded by the European Research Council, the ERC, and also Digital Futures. Let me start by motivating this. How to control a turbulent flow? That's maybe a question that is a bit open and many people have tried to tackle it in the past. We're going to try to follow a certain strategy to solve this question. So if we have here, these are coherent motions in a turbulent channel, so it's a wall-bounded turbulent flow. One possible way to go is to maybe first identify what are the most important parts of the flow, which are here in kind of this light blue thing. So if we first identify in this system that is non-linear and chaotic and complex, what are the most important regions, then maybe we may find a way to try to eliminate the most important regions. And then hopefully with this approach, being able to first select in a very nuanced way what are the most important parts and then surgically being able to target those parts, hopefully we will come up with a quite comprehensive and well-performing control strategy to reduce the drag, at least the turbulent drag, which is what we are talking about here. So that's the outline of my presentation today. First, we're going to be using explainable deep learning to identify the most important regions in the flow. And second, we're going to be using deep reinforcement learning to try to control those regions. Let's start then with the first part, where we identify these light blue guys over here, these important regions of the flow with explainable deep learning. And this is something that we have talked about in the past in the channel. I just want to give a quick recap so that everybody is on the same page. This is a framework developed by Andrés Cremades, published last year in Nature Communications. All the data and all the codes are available online open access, so you can just access everything right away. Just go into the repository of my group. And what we do essentially is to develop a computer vision method, in this case a UNet, a deep neural network, such that having the present state of the flow, these are the three-dimensional fluctuations in U, V, and W, we can predict a future state of the flow. And this future state of the flow is, again, the three-dimensional fluctuation field, typically 5 viscous units into the future, although we have tested that the results are very robust for a broad range of near-wall fluctuation scales. And so for several viscous units, that time interval does not change the results. Once we have that model that allows us to predict the flow in the future, what we will do is remove features from the input. We can remove structures. In today's presentation, we're going to be removing pixels. So we remove pixel by pixel the input and try to see what is the effect of that removal in the prediction of the flow. So that way we can hopefully try to understand and build the important regions in the flow. If we look at it in a bit more detail, this is the explainability algorithm. What we find is the whole process. So we start with the U, V, and W fluctuation fields. These are the three-dimensional fluctuation fields. We use our neural network to predict the future fluctuation fields 5 viscous times into the future. And we compare with our UNet, we make this prediction, then we compare the predicted flow fields with the ground truth, okay, which would be the DNS, the direct numerical simulation data. In our case, that error is less than 1%. We have very, very accurate methods to really predict based on convolutions and basically a UNet, so different resolution layers, trying to really have a good usage of the spatial patterns to predict the flow very well into the future. Once we have the prediction, what we're going to do is remove features from the input. So we will remove pixel by pixel all the elements in the input, repeat the prediction, see how the error changed, and based on how much the error changed, we're going to rank the pixels by importance. We're going to use something called SHAP. These are Shapley additive explanations. This is a game theoretic method designed to enhance the explainability of deep learning models. And those SHAP values are going to be our importance scores. They're going to indicate the importance of each of these pixels in my input. Now, what can I do? I can do that pixel by pixel, and this, by the way, is an extension of the SHAP work from last year. This is together with Andrés Cremades and Sergio Ollas. You can find the preprint here. So go to archive, you can read everything is there. The idea is that we can use those regions of high importance, and with percolation, we're going to select the three-dimensional volumes of highest importance. Those three-dimensional volumes, which you can see here, in fact, this panel that says SHAP, these are coherent structures based purely on importance. These volumes are going to be the ones that we will use to try to understand turbulence a bit better. And you can see how these instantaneous structures look like when they are obtained based on importance. What you can see here are the Q events. So these are structures based on Reynolds stresses. What you can see down here are the typical streaks, the near wall streaks, and here you have the vortices. And remember, the vortices, in this case, they're identified with a Chong criterion. You can use lambda2, you can use many different ways of identifying vortices. This is what people typically visualize. When doing CFD, you show the three-dimensional vortices. Now, what we can see is the importance of each of these structures. In other words, we have the SHAP, and the SHAP are the ones objectively based on importance. And we're going to compare all the classical ones, so Q events, vortices, and streaks, with the SHAP. And the agreement will tell us how important the classical structures are. So this can be done in different ways. The first thing that we do is to look at the joint PDF, the joint probability density function of the SHAP structures. The vertical axis is the inner scale wall normal distance. The horizontal axis is the inner scale stringwise velocity fluctuation. So you can see how the SHAP looks like. We're going to compare it with, from top to bottom, different types of classical structures. So we have the Q events here, the streaks here, and the vortices here. So let's compare. Obviously, there's some similarities in these probability density functions, but there's going to be some differences as well. If you see this region, so this region here close to the channel center and this region here close to the wall, there are some similarities with the Q events. In particular, the region up here looks like ejections, right? There's quite some agreement with the ejections, and the region here shares many similarities with the sweeps, right? So positive stringwise velocity fluctuation and located close to the wall. The similarities don't end up there. If we look at y plus 15, we can see these two regions, both of them with very good agreement with the streaks. When you have a negative stringwise fluctuation, you have a low speed streak. When you have a positive stringwise fluctuation, you have a high speed streak. So there is some agreement also at y plus 15. And even more, if we look at the channel center, this region over here has good agreement with the channel center of the vortices. So if we look at the joint PDFs, if we look at the probability density functions, different regions of the SHAP distribution have different levels of agreement with the classical structures. We can take it one step forward and calculate the one-to-one agreement, the one-to-one coincidence between structures. So basically I have my 3D flow field, I have my SHAP field, I have my Q distribution, and I take point by point the agreement between those structures. And I can express that as a percentage. That's exactly what I show here at the bottom. In the vertical axis, I'm showing you the percentage of agreement between different structures, and in the horizontal axis, I'm showing you the inner scale wall normal distance. There are three important things here. The first one, you can see this region over here in this balloon. What you can see is that at y plus 15, the streaks and the SHAP have over 90% agreement. And then after y plus 15, that agreement basically goes down to 0. So the streaks agree very well with the SHAP at y plus 15. That means that in that location, the streaks are important because they agree with our importance-based structures. If we look at the region close to the wall, you can see this balloon over here. The Q events agree about 70% with the SHAP, and closer to the outer region, we have 70% agreement between the Q events and the SHAP. So once again, close to the wall, we have sweeps being important. Far away from the wall, we have ejections being important. And this again shows that obviously the Q events in different regions of the channel, they exhibit some agreement with our importance-based structures. Even the vortices, if we look at the channel center, which is here, they have about 25% agreement with the SHAP, which is kind of interesting because the vortices is what we typically show when we do visualizations, but their importance is actually quite low. And this kind of indicates that the fact that something is there and you can see it does not necessarily mean that it's important, right? I mean, here, with this data-driven method, we can really define importance in an objective, unbiased manner such that we can really assess what matters and what doesn't matter in the flow. The conclusion of this first part of the presentation is that the classically studied structures in turbulence only paint a partial picture, because the streaks are only important at y+15, the sweeps are only important close to the wall, the ejections are only important far away from the wall, and the vortices are not even so important anymore. Now, this gives us so much power to understand turbulence in an unbiased, objective way, and to really be able to identify causal mechanisms that are relevant in turbulent flows, again, not based on intuition or physical observation, but on data, really on objectively what is and what isn't important in the flow from the data. And this is exactly what we're going to try to take advantage of to do flow control. So this will be the second part of the presentation. Once we identify what are the most important regions in the flow, we're going to use deep reinforcement learning to try to surgically remove those important regions and hopefully achieve a lower drag. So a very quick recap of reinforcement learning, and we have covered this in the channel many times, so I will just be a bit brief. In reinforcement learning, you have an agent, which is our neural network, interacting with an environment, which will be our flow simulation. It could be an experiment as well. That interaction is through actions, and those actions are basically the flow control. In our case, we're going to do blowing and suction at the wall, at the surface of the wing. Once we apply those actions, the state of the system, which is basically the observation that we have of our flow, changes, and also the reward changes. And the reward is a measure of the quality of those actions under a certain norm. Now, this is a model-free reinforcement learning framework, so we're going to be training the neural network to try to maximize the reward through the policy by interacting with the system. So we'll try different actions, we'll see how the policy is giving us different rewards, and we will adjust the parameters of our network such that the policy, which will tell us, given the state of the system, what are the actions to take to maximize the reward, so that that policy is maximizing the long-term reward of our system. Okay? And the reward is going to be a key aspect today in today's presentation. Typically, the reward will be drag reduction, but we're going to explore other possibilities. This is, again, a lot of work by Luca Guastoni, who initiated this in turbulent channels. Also, Colin Vignon has a very nice review paper here on reinforcement learning for flow control. Now, one of the baselines that we're going to be using is opposition control. In opposition control, what we have is basically a system where we're going to be measuring at a sensing plane, basically y+15, that's the usual plane where you're measuring at least at Lorentz numbers, and you're going to measure the vertical fluctuations in such a way that in the wall, we're going to apply a Dirichlet boundary condition with a velocity fluctuation in the opposite direction. So hopefully in that way, the velocity fluctuations will cancel and we will end up with a reduced drag in our flow problem. Now, of course, this is a, well, this is a classical approach, and this is relatively simple because we are just hoping that the fluctuations will attenuate when I oppose those. And with reinforcement learning, we're hoping to discover something a bit more sophisticated, a bit more nuanced. To do that, we're going to leverage this multi-agent reinforcement learning framework. This is, again, work done with Luca Guastoni. Also have a look at this paper with Steve Branton and Beverly McKeon in Nature Reviews Physics, where we really discuss in details how to implement and how to study this multi-agent reinforcement learning framework. MARL for short. In multi-agent reinforcement learning, what you have is a single agent, and that agent is copied into many instances. These are the so-called pseudo-environments, where, because of the periodicity of the flow in the stringwise and spanwise directions, we can have statistically invariant properties in each of these pseudo environments. In other words, the flow is turbulent, chaotic, is doing different things in each of these regions, but statistically is doing the same because the flow is homogeneous in both the stringwise and spanwise directions. So doing so, we can achieve two things. First of all, the same agent is training many pseudo environments in parallel, so we effectively speed up the training. Second, we can have a global reward. Sometimes we can have also a local reward with overlap between two pseudo environments, so that depends a little bit on the case that we want to study. But let's imagine now in this example we have a global reward, and then the agents can cooperate to try to achieve the maximal increase of that reward. And we have shown in some of our work also with Colin Vignon, multi-agent reinforcement learning is the way to go in turbulence. With single-agent reinforcement learning, you can't really beat the curse of dimensionality. With multi-agent, you can really get the agents to cooperate. You can do the training in parallel and really achieve significant results, even in high-dimensional complex systems like turbulent flows. So we leverage MARL, multi-agent reinforcement learning. I'll just show you some of our earlier results from Luca Guastoni in turbulent channel flow. With opposition control, we achieved 20% drag reduction. With reinforcement learning, we achieved 30% drag reduction. So we can significantly outperform the classical control because opposition control at the end is just giving you the opposite fluctuation, whereas with reinforcement learning, you discover something more nuanced, something a bit more complicated. I also want to highlight that, in fact, in this case, and in the cases that I'm going to be talking about today, the training is done in a so-called minimal channel, where the physics is simplified. It's a small domain. You only have one single self-sustaining process in the near wall region of the channel, and then they are deployed in a full channel. Okay, so these results are not in a minimal channel. These results are in a full channel at Arita 180, but the training was done in a minimal channel, which is actually quite interesting how you can generalize the physics, learn a simplified setting to a much more complex configuration. So this first comparison tells me reinforcement learning, there is something there because we can beat significantly the classical opposition control. If we analyze the flow, what we actually see, this is a quadrant analysis. So we are looking at the stringwise and wall normal fluctuations at y plus 15, stringwise in the horizontal axis, wall normal in the vertical axis. At the top, I'm showing you the uncontrolled flow, where there is a predominance of Q2s and Q4s, so sweeps and ejections. In the middle panel, we have opposition control, where what we see is that the fluctuation range shrinks, but the predominance of Q2s and Q4s is still there. And in the last panel, I'm showing you the reinforcement learning, where you can really see a fundamental change in the flow, where there is a quite even distribution of the fluctuations across the four quadrants. Now, this is where the exciting stuff happens. This is a very new work developed by Miguel Benítez together with Andrés Cremades and Luca Guastoni. This is now in archive, so you can see the preprint out over here. Please go there to check all the details. This is really something where we believe we can have tremendous progress in turbulence control. And the idea is the following. We're going to have a similar setting to that, to the one that I showed you before, with the agent interacting with the environment, which is the CFD solver. And what we're going to be changing here is the reward. In the reward, I'm not going to try to minimize the drag. My reward is not going to be drag reduction. My reward is going to be minimization of the sharp structures. So the importance-based elements, the elements that are essential to sustain the turbulence fluctuations, that's going to be exactly what I will target and try to minimize with my reinforcement learning. And I try different configurations. Here, you're going to see the same color code in the next results. So here in orange, you have the opposition control. That's the baseline. In blue, you can see the reinforcement learning for wall shear stress reduction. That's where the reward is to reduce shear. That's what I showed you just a minute ago. Then in purple, I'm going to show you reinforcement learning to minimize Q events. These are the classical Reynolds stress structures. In cyan or light blue, you have the streak reduction in the reward. And this light green, the reward is the minimization of the sharp structures. So this is really the novelty here. We first identify what's most important, then we find with reinforcement learning ways to minimize what's the most important. These are the results. So at the top, I'm showing you the drag reduction as a function of time for the various cases. And you can see in this column over here the drag reduction from the various approaches. Just to highlight the most relevant things, here in dark blue you have the reinforcement learning for wall shear stress reduction, 31.7% reduction of drag. And in light green, at the top, you can see the arrow here to help you find the right line. You see the one where the reward is the sharp extractors. You can see two things. The first one is that we have higher drag reduction. We have 5% more drag reduction than with the wall shear stress. And the second, you can see the oscillations. The oscillations are very small. You have a much, much better control of the state of the flow with fewer fluctuations, with a more robust way to really deploy the control than with the wall shear stress for drag reduction. So the top performing method is when we target the most important extractors. Here at the bottom, you can actually see that if we're looking at how we are reducing streaks and Q events, the policies that reduce the Q events and the streaks more are not the ones that reduce the drag more significantly. So that also indicates and confirms the stuff that I talked about at the beginning, that the classical extractors are not the most important. The most important is the SHAP, which is what we identify based on our explainable deep learning algorithm. Another important result here is the cost of the control. If we look at the net energy saving, and the net energy saving, you look at the skip friction reduction, but you also discount the power required to drive the control, right? Because, okay, sure, we're reducing the drag, but if we need a lot of energy to reduce the drag, then we might be in a situation where things are not worth it for us. And you can see in light blue, this is the streak reduction. In dark blue, the line over here, that's going to be the reinforcement learning for shear stress reduction. And in green, the reinforcement learning for SHAP reduction. The power required to control the flow when I target SHAP extractors is half of the power required when the reward is shear stress reduction. So the net energy saving goes up to 5.4% better, comparing the SHAP and the reduction purely of the wall shear stress. So not only we get a more stable control and a higher drag reduction, we also need half of the energy. So obviously, when this is deployed experimentally, which is the next step for us, that is going to be much more beneficial to use the SHAP-based extractors, the SHAP-based control, than just purely and almost naively reduce the drag with the reinforcement learning algorithm. There is a bit of an overview of other reinforcement learning cases in Turbulence where we are leveraging multi-agent reinforcement learning and some very exciting stuff that we are developing. Here you can see some work with Bernat Font, Francisco Alcantara-Avila, Oriol Lemcoul, Jean Robot, people from the Barcelona Supercomputing Center, where we use reinforcement learning to reduce separation. We perform much better than periodic control, and RE-tau is 750, so this is actually a quite higher Reynolds number. This is just published in Nature Communications, so feel free to reach out and ask questions if you have any questions. This is a very, very nice result. Here we have with Paul Suarez a lot of fantastic work on cylinder flows in 2D and in 3D. So we see that as the flow gets more three-dimensional and more chaotic, the reinforcement learning strategies manage to tackle those instabilities in the wake. So again, much better performance with reinforcement learning than with periodic control. And here at the bottom, some work led by Joel Bassanth, where what we do is reduce the Nusselt number in three-dimensional Rayleigh-Bénard conversion. So in this problem, what we want to do is reorganize the convection cells into this more stable configuration where the convective heat transfer is actually reduced. So lots of potential, lots of exciting things happening with reinforcement learning for turbulence control. And this is a little overview of what I talked about today. First of all, with SHAP, we can identify the most important structures in the flow. For turbulence, this is an open problem. This is a very important question to try to get physical insight into turbulence. Second, with reinforcement learning, targeting the shear stress, we can reduce 30% the drag, and that's actually very good. But crucially, and more importantly, when we use SHAP combined with the reinforcement learning, we can target the most important structures of the flow. We get the highest drag reduction with a very low energy input. So this is really the way to go in the future, where we can really target the important structures in the flow and basically break the important causal mechanisms inherent in near-world turbulence. As always, all the codes, all the data are available open access in this repository, so feel free to go there, feel free to reach out if you have any questions, always happy to discuss. And this is a great effort thanks to InfraVis and also the KTH Visualization Studio to make this video happen. As always, I'm available to discuss. If you have any questions, that's all I have for today, but I'll see you in the next video. Thank you and bye.